Welcome to the deep dive. Today, we're cracking open the hood of your devices. We're going to explore the fundamental building blocks of how computers, well, how pretty much everything that calculates processes information.
That's right. We're diving into a document here that really zeroes in on computer components and specifically processors.
So our mission really is to unpack the core ideas behind how these brains are designed.
Yeah, we'll look at different structures, see what makes them tick, and why some are perfect for, say, the simple chip in your fridge, while others are needed to power your laptop or even a massive supercomputer.
Understanding this stuff really does demystify the digital world around you, doesn't it?
It absolutely does. It shows the clever sort of foundational logic behind these complex machines.
And speaking of foundations, let's start with a really big one that's highlighted in our material. This revolutionary idea from way back in the 1940s, credited to brilliant minds like John von Neumann and Alan Turing, the stored program concept.
Right. Such a huge leap. Before this, computers were often, well, hardwired for specific tasks, or you had to manually reconfigure them.
Imagine rewiring your machine just to run a different calculation.
Exactly. The stored program concept changed all that. The core idea, really, is that the instructions for a computer, the program itself, can be stored in the same memory as the data it's going to work on.
So the program isn't fixed hardware anymore, it's just data
Yeah.
sitting in memory.
Precisely. It's a sequence of instructions loaded into the main memory. The processor then fetches these instructions one by one, figures out what they mean, it's the decoding part, and then carries them out. Sequentially, usually.
Sequentially, one after the other.
Yeah, the flow is generally linear.
Yeah.
But programs can include instructions to jump to a different point in the sequence. That allows for things like loops, decision-making, conditional logic.
Okay, so the program lives in memory with the data, and the processor just steps through it unless told to jump. That really is fundamental to modern computing. And it leads us straight to the main ways processors are actually architecturally designed to implement this concept.
Correct. The document we're looking at focuses on two primary architectures. The von Neumann architecture, which you probably encounter most often, and then the Harvard architecture, which is an alternative model with, well, different priorities.
Let's dig into von Neumann first then. Since it's the most common way to do that stored program thing, how does it handle the memory and the instructions?
Okay. Its defining characteristic, the key thing, is that instructions and data are stored together in a common main memory. And crucially, they share a single bus for transferring information back and forth between that memory and the processor, that
A
is.
single bus. Okay, so like a single road, everything has to travel on it, data, instructions, the works.
That's a great way to think about it, yeah. A
Yeah.
single shared pathway. And this is why you find the von Neumann architecture in pretty much all general-purpose computers today, your desktop, your laptop, servers.
Right.
The document highlights its big advantages. It's cost-effective, it's simpler to program for. The control unit inside the processor is also less complicated to design because it only have to manage that one bus. And memory and input-output devices are accessed in the same way.
And because they share that space.
Exactly. Because data and instructions share the same memory space, they generally use the same basic word length. The size of the data chunks the processor handles.
Okay, that sounds efficient from a design perspective, cost perspective. But that single shared road seems like it could get jammed up, right?
It absolutely can. That single bus is noted as the primary bottleneck for the von Neumann architecture. It's often called the von Neumann bottleneck.
Ah,
If the processor needs to fetch an instruction and also read or write a piece of data around the same time, they have to sort of wait their turn to use that single pathway. That can definitely limit performance, especially as processors get faster and faster.
Okay, so von Neumann. Shared memory, shared bus, great for flexibility, great for cost, but potentially bottlenecked by that single path. So how does Harvard tackle this?
Harvard takes a completely different approach. Instead of sharing, it separates. Data and instructions are stored in separate memories.
Separate memories.
And because they have separate memories, they also use separate buses for their transfer.
Okay, so now we have two dedicated roads, one just for instructions, one just for data.
Exactly that. And the big win here is speed. With separate buses, instructions and data aren't competing for the same path anymore.
Right.
The processor can potentially fetch the next instruction from its memory using the instruction bus at the very same time it's reading or writing data to its data memory on the data bus.
Oh.
This parallel access is a major performance booster.
That makes intuitive sense. Parallel operations are usually faster. So where do you typically see this Harvard architecture then?
You often find it in specialist embedded systems. Think of the chips controlling your microwave, maybe some smartwatches, automotive systems sometimes. It's particularly common in digital signal processing chips, DSPs.
DSPs, right.
Yeah, where processing data streams in real time is absolutely critical.
Yeah.
Speed is paramount there, sometimes more important than, say, the simplicity of the design.
And they can have different memory sizes, too.
That's another key feature, yes. Those separate memories can even have different sizes or different word lengths optimized for whatever they're holding instructions or data. The trade-off, though, is that you can't use spare data memory to store more instructions, or vice versa. They're separate pools.
So it sacrifices some of that von Neumann flexibility, and it sounds like it adds complexity, all for the sake of speed in certain specific tasks.
That's it, exactly. The control unit needed to manage two independent buses is more complex, and therefore generally more expensive to build compared to von Neumann's single bus system.
Given those trade-offs, then, do modern computers just pick one and stick with it? Is it strictly von Neumann or strictly Harvard?
Not really, no. Contemporary processors often blend aspects of both. It's quite clever, actually. The document points out that while your main system memory, the big pool of RAM, might follow the von Neumann model shared pool for everything, the incredibly fast cache memory sitting right next to the CPU is frequently divided.
Divided how?
Into an instruction cache and a data cache.
Oh, okay. So inside the CPU, that super fast cache acts more like a Harvard system to speed up access to the stuff it needs most often.
Precisely. Retrieving information from the cache uses those Harvard principles, separate paths for instructions and data for speed, even though the larger main memory behind it is von Neumann. And some really high-performance processors, like certain DSPs, might even have multiple parallel data buses, maybe 2 for writing, 3 for reading, and a separate instruction bus. It's a clear hybrid approach, aiming for maximum throughput. They really take the best ideas from both to optimize performance where it counts the most, like right there inside the cache.
That's fascinating how they mix and match these foundational ideas. Okay, so beyond how memory is structured, processors also differ in the actual language they understand, right? Their instruction set. And this brings us to another core distinction mentioned in the material, CISC versus RIC.
Right. This is basically about two opposing philosophies for designing the set of commands a processor responds to. CISC stands for Complex Instruction Set Computers.
Complex. Okay, the name gives it away.
It does. As the name implies, they use a large, varied set of instructions. The goal here, historically anyway, was to make each individual instruction do a lot of work.
So one single instruction could trigger a whole sequence of internal steps, like a mini program within the instruction.
Pretty much, yeah. They aim to accomplish tasks in as few lines of assembly code as possible. The document gives a great example, a single MULPA B instruction in a CISC design. That one command could potentially trigger the hardware to load the value from memory location A, load the value from memory location B, multiply them together, and then store the result back into memory location A.
All in one go.
All in one instruction. It integrates operations like loading and storing with the calculation itself.
Wow, packing all that into one instruction sounds like it would make programming quicker, especially back when assembly was more common.
It did. The advantages highlighted are, well, quicker coding because you're writing fewer lines for a given task, and the compiler, the software that translates your high-level code like Python or C++ into machine code has less complex work to do because there's often a direct CISC instruction that matches a high-level operation pretty closely.
Makes sense.
The document also mentions that historically, because the code itself was shorter, fewer instructions needed, it required less of that precious RAM to store the program, and RAM used to be really expensive. That was a big deal back then.
Okay, so CISC, complex, powerful instructions, leads to fewer lines of code, needed less RAM historically. Got it. What's the RIC philosophy then? It sounds like the opposite.
It is. RISC, or Reduced Instruction Set Computers, takes the completely opposite approach. Instead of those complex multi-step instructions, it uses a minimum number of very simple instructions. The core design principle is that each instruction should be basic, really fundamental, and ideally execute in just one tick of the processor's clock.
One clock cycle. Okay, so that MULTA B example would look very different on an RISC machine.
Totally different. The document breaks it down nicely. In a typical RISC system, you'd need multiple separate simple instructions to do the same thing. First, you'd need an instruction to load the value of A from memory into a temporary storage spot inside the processor called a register. So maybe LDA R1, A.
Okay, load A to register 1.
Then you'd load B into another register, LDA R2, B. Then you'd perform the multiplication, but only between the registers. MULT R1, R2, perhaps store the result back in R1.
Multiply the registers.
And finally, you'd need another instruction to store the result from the register R1 back out to the memory location A, STO R1, A.
So what was that? 4 simple instructions instead of one complex one. That seems like more work, especially for the compiler to generate all those simple steps.
It is more work for the compiler, absolutely. But it comes with some significant advantages, especially in the hardware. The document points out that because the individual instructions are so simple, the processor hardware required to actually execute them is much simpler to build. It needs fewer complex circuits.
Simpler hardware.
And crucially, because each instruction ideally takes the same amount of time, that one clock cycle, powerful speed-up techniques like pipelining become much, much easier to implement effectively.
Pipelining. What's that exactly?
Think of it like an assembly line for instructions. While the processor is, say, executing instruction number 3, it can simultaneously be decoding instruction number 4 and already fetching instruction number 5 from memory.
Overlapping the steps.
Exactly. By overlapping the different stages of processing an instruction, fetch, decode, execute it, can complete instructions much faster overall, even though each individual step is simple. It's about throughput.
Okay, that makes sense.
And the document also notes that the historical advantage CISC had with needing less RAM, well, that's largely faded. RAM is incredibly cheap now compared to how it used to be. And the performance gains you get from RISC's simpler hardware, that effective pipelining, and highly optimized software often allow for better performance processors at a lower overall cost these days.
So it's a real trade-off then. CISC simplifies the software and compiler's job, but you pay for it with complex hardware and maybe bottlenecks within those complex instructions. RISC, on the other hand, simplifies the hardware, relies more on the compiler to break things down, but gains speed through things like pipelining, especially now that RAM isn't such a constraint.
That's a great summary of the core difference in philosophy, yeah. And, while we've mostly been talking about architectures and instruction sets for a single processing unit, modern performance gains come hugely from going beyond just one core.
Right.
Which brings us nicely to the world of multi-core and parallel systems.
The idea of putting multiple processor brains effectively onto one single chip. This feels like a pretty natural progression, just trying to do more things at once.
It really is. Multi-core processors are designed specifically to distribute the workload across several processor cores that live together, usually on one piece of silicon. By doing this, they can execute multiple tasks or even multiple parts of a single large task simultaneously, or, in parallel.
Which is why they're often just called parallel systems.
Exactly. Your personal computer, your phone, your tablet, they're very likely dual-core, quad-core, maybe even octa-core or more now, meaning they have 2, 4, 8, or even more independent processing units inside.
And supercomputers just take that to an extreme.
Oh yeah, they scale it up dramatically. Supercomputers can contain thousands, even tens or hundreds of thousands of cores, all working together.
But the document mentions you need more than just the hardware, right? Having multiple cores isn't magic.
That's an absolutely critical point. The software you're running must be designed, or at least compiled, to actually take advantage of multiple cores. If a program is inherently sequential, step 2 absolutely must wait for step 1 to finish, and step 3 waits for step 2, then just throwing more cores at it won't make it run any faster.
Because only one core can work on it at a time anyway.
Right. The task itself, or the collection of tasks, has to be breakable into parts that can genuinely be done independently, in parallel.
Can you give an example of software that does this well, something we use every day?
Web browsers are a prime example highlighted in the material. Applications like Chrome or Firefox are designed to run different processes concurrently. Think about it. When you have multiple tabs open, different cores can simultaneously handle processing the requests for different websites, maybe rendering a video in one tab, running some complex JavaScript in another, keeping the user interface responsive in a third. It's all happening at the same time. That naturally parallel structure makes browsers great candidates for benefiting from multi-core systems.
That makes a lot of sense. Browsing really is a bunch of semi-independent activities happening at once.
Okay, so multi-core is one way to boost performance. What about other ways systems add specialized processing power?
That leads us neatly into coprocessor systems. A coprocessor is essentially an extra processor that works alongside the main CPU, but it's typically designed for very specific functions.
So it's like a specialist helper chip. Not trying to do everything, just really good at one or two things. Precisely. It's not meant to run general programs like your operating system or word processor. Instead, it's highly optimized for a limited range of functions, where it can be much, much faster and more efficient than the general-purpose CPU trying to do the same thing.
What kind of functions are we talking about?
The document mentions examples like handling complex math, especially floating-point arithmetic, graphics processing, which is a huge one, or digital signal processing.
And the most famous modern coprocessor is probably the GPU, right? The graphics processing unit.
Absolutely. The GPU is a perfect example. It's a specialized electronic circuit that is incredibly efficient at manipulating computer graphics and image processing. While the document covers coprocessors generally, it definitely highlights GPUs because they're so prominent now.
What makes them so darn powerful for graphics? What's different about them?
It really comes down to their architecture. Instead of having, say, 4, 8, or maybe 16 large, complex, general-purpose cores like a typical CPU, a GPU consists of thousands of smaller, simpler, but highly efficient cores. And these cores are specifically designed for parallel processing.
Thousands. Wow.
Yeah, this massively parallel architecture lets them just crunch through huge blocks of visual data simultaneously, which is exactly what you need to do to render detailed 3D game worlds or process high-resolution images rapidly.
And you find these on graphics cards in PCs.
Traditionally, yes, in a PC, you'll often find the GPU on a separate graphics card. But they're integrated directly onto the main chip in many other devices now, too.
So just to recap that difference, CPUs generally have fewer but more powerful and flexible general-purpose cores. GPUs have tons and tons of simpler, specialized cores designed for doing similar calculations on lots of data in parallel.
That's the core idea, yes. And while they were born from the needs of graphics, the document notes that GPUs are increasingly used alongside CPUs to accelerate all sorts of other applications now. Things like scientific computing, engineering simulations, AI and machine learning training. Anywhere you have tasks that can be broken down into many, many independent parallel operations. That massively parallel structure is useful beyond just pixels.
And you said they're not just in gaming PCs or workstations anymore.
Definitely not. They're essential for driving the displays and user interfaces in your mobile phones and tablets, but they're also showing up increasingly in cars, for navigation systems, infotainment, even driver assist features. You find them in drones for real-time image processing, in robots for computer vision and control systems. Basically, wherever you need efficient parallel processing of data streams, especially visual data, a GPU or a similar kind of parallel coprocessor is likely involved these days.
So bringing it all together for you, the listener. Wow, we've covered a lot of ground. We've seen how that fundamental idea of a stored program gets implemented in different ways. The shared memory and bus of von Neumann, which is great for general use, but has that bottleneck.
Right.
And the separate memory and buses of Harvard, which is great for speed and specialized systems. And then how modern chips cleverly blend these, especially in their cache memory.
Then we looked at the two main philosophies for the instructions themselves.
Yeah.
CISC, packing a lot of power into complex instructions.
Which was good when RAM was scarce.
Exactly. And RISC, using many simple instructions that enable faster hardware techniques like pipelining, which often wins out today.
And finally, we saw how performance really scales dramatically now by using multiple cores working in parallel. Whether that's a few general-purpose cores in a CPU juggling your browser tabs, or those thousands of simpler, specialized cores in a GPU accelerating graphics or complex scientific computations.
And all these design choices, the architecture, the instruction set, the approach to parallelism, they represent constant trade-offs, don't they? It's always about balancing cost against complexity, speed against power consumption, and matching the design to the specific job the processor is ultimately intended to do. Every single device you use has these underlying principles shaping its capabilities.
It really highlights the incredible engineering and, the clever compromises that are made inside these tiny, tiny pieces of silicon.
It really does. It's quite amazing when you think about it.
So as we wrap up this deep dive, we've journeyed from that foundational stored program concept right through the von Neumann and Harvard architectures. We've explored the competing philosophies of CISC and RISC instruction sets, and we've seen the immense power unlocked by multi-core processors and those specialized coprocessors like GPUs.
We've touched on those core distinctions.
Yeah.
Shared versus separate memory and buses, complex versus simple instructions, and the whole concept of distributing tasks across many cores to get more done faster.
And we've seen how these different approaches are matched to different needs, from your everyday computer or phone to the tiny embedded systems maybe in your home appliances, all the way up to those high-performance machines crunching data for science.
It covers a huge range.
Absolutely. So Building on the trends we've discussed from the material, this blending of architectural ideas like von Neumann and Harvard and Cache, and the undeniable rise of powerful specialized coprocessors for things like graphics, AI, parallel computation in general. Here's a final provocative thought for you, the listener, to maybe mull over. Given this clear direction, what might the computer processor of the future ultimately look like? Will we see even greater fragmentation with maybe hyper-specialized chips for AI, separate ones for graphics, dedicated ones for communication, networking, and so on? Or will the general-purpose CPU continue to evolve, maybe integrating more and more of these specialized functions onto a single, incredibly complex chip, finding new ways to balance that general flexibility with extreme task-specific efficiency?
It's a fascinating question. It's such a dynamic field, always pushing the boundaries of what's possible.
It really is. Well, thank you for joining us for this deep dive into the fascinating and fundamental world of processor design.